Exercise 7 of Chapter 5 is focused on empirically confirming the live evil rule. Now, I don't know if the live evil rule is my favorite rule in all of linear algebra, but it's probably the one that I like talking about the most, just because of the name. So what we are going to do in this exercise is confirm the live evil rule using a set of matrices. So matrix L of size 2 by 6, and these are all random number matrices. Matrix I of 6 by 3, V 3 by 5, and E 5 by 2. So what we want to do is first multiply these four matrices, and then the product of those matrices is transposed. So that's step 2. Step 1 was to create these matrices. Step 3 is to transpose each matrix individually and then multiply them without reversing their order. So L transpose times I transpose times V transpose times E transpose. And then step 4 is to transpose the matrices individually and multiply them in with reverse order. So then it's E transpose times V transpose times I transpose times L transpose. And then we'll see what happens after that. And then finally, we're going to repeat all of these steps, but using square matrices instead of rectangular matrices or non-square matrices. And maybe I'll make them all 4 by 4, just to pick a number. Okay, so I hope you enjoyed working through this exercise. Now I'm going to switch to Python. I will show you my code. So this was step 1, pretty easy. Just create random matrices of the sizes specified in the text. Okay, and then let's see. So we need this one first, res2. Okay, so I have result 1, which is the product of these four matrices, and then that product is transposed. And then res2 is each individual matrix transposed and then multiplied in exactly the same order. And actually, before I do this line, I'm going to run this just to show you that there's no errors. So every line of code, all 5 lines of code that I have here are perfectly fine. No errors, no bugs, no warning messages or anything like that. Okay, so then let's see if these two matrices are equal to each other. And the answer is, not only are they not equal, we cannot even compute the matrix product here. And that's because once we start inverting things, the matrix dimensions no longer are valid for multiplication. For example, L times I, the inner dimensions are 6, so that's fine. But L transpose times I transpose means that the inner dimensions are now 2 and 3 once you transpose these two matrices. So those are not equal, so even at this very first step, this is not a valid multiplication. Okay, so then let's try it with result 3, where we are reversing the order of the matrices. So here's L, I, V, E. Okay, and we can see two things. First of all, that the code actually ran, so there's no errors, there's no warning messages. And we see that the result is, within rounding error tolerance. We can consider these to be basically zeros. And so, so we can say that these two expressions are the same as each other. In other words, an operation applied to the product of matrices can be applied to each individual matrix, and then you have to swap the order. Now, that is not trivially always true. It is trivially always true with the transpose operation because every matrix can be transposed. You will see later in the book that there are cases where, the product of two matrices can be inverted. So we can apply an inverse on that product, but the individual matrices cannot be inverted. So when the operation is valid on the individual matrices, you have to swap the order. Okay, so then the last thing that we wanted to do in this exercise is change all of these non-square matrices into square matrices. So they're all 4 by 4 matrices. Let's start again with res 1 and res 3. And we see, again, all zeros or, tiny, tiny numbers that we can basically just ignore. Okay, now remember, before res 2, actually, let's just see if this even runs, right? Because remember, before, it crashed here. It just didn't work. It was not a mathematically valid expression. So this is interesting. Now it does work. in the sense of, we haven't checked yet whether res1 and res2 are equal to each other, but it works in the sense that this is a valid mathematical operation. Okay, and now we see whether these are equal to each other, and they are definitely not equal to each other, not even close. This is not something we would consider to be zero within rounding error tolerance. This shows that this result and this result are completely different matrices from each other, and that's because L and L transpose are two distinct matrices. They have the same elements, but they're swapped, so they are not the same matrix. So when we transpose them, they become different, and multiplying them, therefore, is an entirely different beast altogether.